Hi everyone. Today what we're going to walk through is it's almost a little bit of a review day. What I want to do is I want to spend some time getting a quick little review problem, if you want to look at it, for problem 1 that you see on your screen. But also, let's just spend some time breaking down some components of some trig functions and working our way through on if we have the picture, the graph of a trig function, can we go through and build the equation that would represent that? So today should be a little bit of a smoother day, but it's really going to lay the groundwork for our last lessons in this unit. So I'd like everybody to pause the video now. Let's use problem 1 on that page, on the screen, as a review problem for Are You Good with Solving Trig Equations? Pause it now. Okay, we should be back. And so I would hope that when we take a look at this problem, we kind of have a sense. It's not needed, but maybe we have a little bit of a sense that since I see tan in that problem, I know that cos x cannot equal 0. That would make that function undefined, or sorry, that equation undefined and therefore not true. So we've just got that maybe floating in our mind. Whether you put that down or thought about that, though, isn't that important right now. My guess is, though, the idea that we had two different trig ratios was probably not useful. And so you replaced your tan with sine over cos. We were then able to go through and multiply out our cos value, multiply every term by cos. To eliminate the denominator was probably an action we took. We then notice that we have sine x and cos squareds, and we do know that we can replace a cos squared with 1 minus sine squared, and this will eventually get us down to having one trig function or trig relation. So maybe we spent a line doing this, I don't know. Perhaps we could already see what was going to happen, and so we thought about everything being on the right side of that 0. So I have a positive 2 sine squared, a negative 3 sine x, and a negative 2 equaling 0. We take a look. Hopefully that thing factors because we can't put those signs together. When you look at that, we need two numbers that multiply to give 2, two numbers that multiply to give 2. If I have a negative and a positive, then I can get to my negative 3. That thing is going to factor. And so it factors into a 2 sine x plus 1 and a sine x minus 2. That then is going to allow us to solve for the ratios. And so we know that sine x equals negative 1/2 or sine x equals 2. Very quickly, we're probably pretty good to be able to label that sine x equaling 2 as no solution, because I will not be able to solve that. And therefore we are able to go through. Maybe we're even at the point, as we stated earlier, where we don't need to write or draw the picture, but instead we can see that sine is negative, so we know we're down. And since that's my opposite side of negative 1, hypotenuse of 2, then we can see that we have pi by 6 related acute angles. And so therefore, x is going to give me a 7 pi by 6 in the third quadrant, or an 11 pi by 6 in the fourth quadrant. But since there was no restriction up here, I'm solving for general statements, so I need to give all possible solutions, and there we go. So hopefully we match up. We were able to work our way through, and I think that would be a great gauge for us of do we have what we need from our trig equation day. Okay, let's jump into the meat of what we're going to tackle today. As you take a look at your screen, all I'd like you to do is just to go through and state a couple key properties for that function. So if you're feeling super confident, then I'd like you to pause the video and work your way through A. Okay, so those people are back. We're going to work our way through A together then. Maybe you're using this simply as a check. So the first thing that we should notice is that we have an amplitude of 5. Please don't have negative 5. Remember, amplitude is half your height. and we're not going to have a negative height. So my amplitude is 5. I can see it as my leading coefficient. My period, maybe we took a look at that period and we said, I recognize what a 2 is going to do. When it's multiplied on the inside, that means I have a horizontal stretch by a factor of 1/2. And so my normal period on my sine curve is 2 pi. Therefore, stretch it 1/2. However, can we please make sure that we keep that best friend at our disposal, that our period is equal to 2 pi over k, and we recognize that we could refer to that 2 as a k value. Phase shift, we have none because there is no horizontal shift on that graph, but we do notice that we are shifting 3 units up. So if that brings back some stuff that makes you feel a little more confident to work your way through, then I'd like you to pause the video now and give B a shot. Okay, and we should be back. So a couple key things. Amplitude of 3 should be good. We can see our k value in here being a 4. And so my normal cos has a period of 2 pi, so I have a horizontal stretch by... Well, if we don't even want to work through that, we know that our period is 2 pi divided by our k value. And so when we reduce that green relationship, we can come in on our pi by 2. Phase shift, this is going to be the most common mistake. And we're really going to get a bit of a test of, did we remember to factor out that k value, or that stretch factor, from everything on the inside of our function? That only when we do that can we interpret our phase shift, and you can then see your phase shift here. So therefore, what is our phase shift? Well, our amount that we shift is pi by 4, and our direction is to the right. Lastly, we should have 1 unit down as our vertical shift, and that should give us some confirmation of, can we identify key features of that graph from its equation? Okay, let's get to kind of the meat of where we want to spend our time today. Can we go backwards then, and given a graph, can we go through and produce the equation? So as you take a look at the instruction for 3, I would like you to write a sine and a cosine function for the graph that we resemble. Now, it came through maybe a little fuzzy. I'm not sure if it's as fuzzy for you, but what we end up having here is a pi by 8 value. We then have a pi by 4 value, a 3 pi by 8, and a pi by 2. So just to make sure that we're really clear and we can see that picture. So I'm just going to jot down what I would argue to you should be a starting point, that we understand what the generic equation to a trig curve could look like that being, I could have some coefficient on a sine or a cos. This is clearly could be represented by one of those things. I then have to determine what is a horizontal stretch, is there a phase shift, and then do I have a vertical shift? So if we're able to go in and complete the components of that, we have to make a choice on sine and cos. I need to have my variables, so my y and my x in there. That means that I need to come up with an a k, a b value, and a c value to be able to complete that equation. I want to draw your attention, though, that my choice of sine or cos will impact whether I have a b value at all or what that b value is. So let's take a look at that graph and let's break down what I have underlined in red. Can we come up with those properties? So the first thing maybe I notice, my amplitude. Well, I know that my amplitude is half my height. So if my curve goes all the way up here from 2 all the way down to -2, then my curve has a height of 4, therefore an amplitude of 2. Okay, if I get to my k value, well, I know that my k value, I have that special relationship of period is 2 pi over k. Some people will go straight to using that. Others can kind of look at that curve and say, I can see one complete cycle And I can see how long it takes to complete that. Pi by 2. And so if they think about the normal period of that sine curve or cos curve of being 2 pi, and this period is now pi by 2, you can start to think about what would you do to 2 pi to change it into pi by 2, and you notice that you would have to have a horizontal stretch by a factor of 1/4. That then means that our k value would have to be 4. Now, for anybody who feels a little nervous about that, we can come back up to our green relationship and we can solve by stating our period we can see on our graph is pi by 2. And now I can solve for k. Maybe I divide out a pi on both sides. I can multiply my k out, so I get k. But then at the same time, let's multiply the 2 out, and I get a k value of 4. So even if we want to kind of put the blinders on a little bit and solve for it, we can. Okay, the last thing I need to solve for is that decision on B. I'll skip over. I need to solve for C. And so as I take a look at C, my vertical shift, well, I know that the middle of my graph is the equation of my axis, and the equation of my axis is my vertical shift. So when I look at this curve, to go the amplitude 2 down or 2 up from the top or the bottom puts the middle of my graph at 0. I can see it on my graph. And therefore, I know that I have had no vertical shift. Okay, I want to come back to the decision and how we find our phase shift. Well, first off, I think I would always want to build the equation that would require the least amount of work. And what that means in our head, I don't know. But for me, what that means is if I can avoid a phase shift, I'm going to avoid a phase shift. And so I think about the starts of my graphs. I know that my sine curve always starts in the middle and rises. I know that my cos curve always starts at the top and falls. And so if I follow those patterns, then I want to look at the graph that's been given, and I'm going to choose my sine or my cos based on which one matches the starting value. And we should see in this instance, my sine curve matches the picture that's given. And so my decision then would be, I'm going to create a sine graph first. Okay, so if I build a sine graph, then I need to have an amplitude of 2. I then need to have a k value of 4. But because I chose my sine curve, which is where my graph normally begins, in the middle, then I do not need a phase shift at all. I also don't need a vertical shift. I've solved that for my c value. That has no bearing on because I chose my sine. So I'm clearly not going to write a plus 0. There is one equation for that graph. Now, the instructions said I have to write an equation for both. So what I'm going to do then is I'm going to create my equation now as a cos curve. So whether I choose sine or cos is going to have no bearing on the amplitude. It is going to have no bearing on the period, so a horizontal stretch, but it will have an impact on the placement of the curve. Horizontally, I'm going to have to now figure out what a phase shift would be. So what I'm going to do on my graph is I'm just going to erase an awful lot of those colors because I want to make sure that we can see this clearly. I know that if I try to match up my cos graph, so now I'm focusing in on my cos curve. My cos curve normally starts at the top and falls. And so what I want to do is I want to look, well, where is the top of my graph on the graph that was given? And I notice that that exists right here. So if I was to then shift my curve to the right 3 pi by 8, then I would now have my graph starting at the top and falling, and it will match up with the graph that's given. So as I take a peek at that then, I can now have a shift right, which means I need a subtraction, the amount, 3 pi by 8, and there is a possible graph. If I was to give you this problem after you've done some practice, I would expect to see both of those equations. However, because these functions are periodic, there is an unlimited number of problems for us. So as we take a peek at that then, what I want to make sure we're good with is you could have come up with this equation as well. That maybe instead of a positive cos curve, you chose a negative cos curve. That means we're going to have a different phase shift. So a negative cos curve means that we are reflected in the x-axis. And so rather than starting at the top of our curve, we start at the bottom and rise. So where does this graph that was given start at the bottom and rise? All the way over here. And so I could have then shifted my curve all the way to the right. Oops. Sorry guys, I goofed up on a number here. If I look back up onto my graph, and I hope that this really didn't confuse anyone, that was a pi by 8. Pi by 4, 3 pi by 8. So this blue phase shift should have just been a pi by 8. And there we go. My yellow phase shift would have been shifting all the way over to a 3 pi by 8 units. And there we go. Hopefully that mistake on my part didn't cause us any confusion in understanding and that everything matches up. So let's jump in and let's keep playing around with some of these problems as we get better and better at it as we go. So as we take a look at the graph that was given, what we want to be able to do is, can we break down finding a few key properties? Can we find an amplitude? Can we go through and can we find a stretch factor, so a K? Can we find a vertical shift? If needed, depending on decision, can we then go through and find a phase shift? So what I'm going to ask you to do is to find 3 properties, those blue properties, given that graph. So let's pause the video now, go ahead and find those. Okay, we should be back. So as you take a look at that graph, we notice that we have a max of 5 and we go all the way down to a minimum of -1. That's going to make the height of that curve 6 units and therefore my amplitude 3. Okay, if I have to take a look at how long does it take to repeat? Well, my graph seems to go from a 2 up, past 2, back, and return to 2 in that time span. So if I scan, what was the distance that took? That was from 0 to 2 pi by 5. I know then that my period is 2 pi by 5. So maybe we look at it as a horizontal stretch and we say my normal period is 2 pi. So to get a period of 2 pi by 5, I need to divide that by 5. And therefore, my K value needs to be 5. Or we go back and we use our best friend. That if we look at that and we say, well, I know that my period is 2 pi by 5, then I know that my period is always 2 pi divided by K. And hopefully we can see that K equals 5 to make that true, or at the very least, we're multiplying out and then solving for K and we're good. You take a look at finding your C value. Now this is one where I would always kind of say, don't trust your eyes so much. You've already made a determination, use it. You've determined that the amplitude is 3. So let's travel up 3 from the bottom or down 3 from the top, and that's what's going to get us to the middle of our graph, and we notice that the middle of that graph is at 2. And so if I was to build the equation of my graph, then they would look like this. I could now have a sine curve that would have an amplitude of 3, a stretch factor of 5. I don't know whether I'm going to need a shift or not, but I will shift it up 2. Or what I have is I have a cos graph that has an amplitude of 3. I need a k value of 5. I'm not sure what a phase shift is, if it even includes one, and a shift up 2. That now as we try to take a look at that graph, we're going to have to consider, well, do I want to use a sine or a cos curve? And then when I use the other one, do I have a phase shift? So as we take a look, we've determined that 2 is the middle of the graph. So when I come back and I look at this 2, I notice that my graph starts in the middle and rises, which is just like a normal sine curve. So I'm going to want to use my sine equation first, because that means I do not need a phase shift. So as I clean up that equation then, I could simply state that it's 5x and add on your 2. Now for a cos graph though, that means I'm going to have to do is a phase shift. So as I did before, I'm going to clean up all that writing I did on the page, because where does my cos graph normally start? It normally starts at the top and falls. Whereas the first time that this graph is at the top and falling, right here. So therefore, I have to shift my curve across that distance. I look down and I notice that distance would be pi by 10, and so I have a phase shift right pi by 10. Okay, what I'm going to do is I'm going to actually go through and build 2 other equations, because I do think that there's actually like 4 equations that can all be seen on the graph given. Okay, the first thing, let's jump back to our green equation. Let's go back to the decision to use sine, because just like using a negative cos graph, I could have used a negative sine curve. That wouldn't change the 5, but it will require a phase shift. So if I wanted to use a negative sine curve, and I'm not saying you would, but if I wanted to, how would I build that one? Well, I know negative sine curves would start in the middle and fall. So where's the first occasion where we're in the middle and falling? Right here. That means that I would have to shift that to the right that distance. And when we look down, we notice that distance would be a pi by 5, so I would then have to shift to the right pi by 5. And there we go. Now, what if we ended up going through and dealing with a negative cos graph? Well, I'm just going to clean up that graph again, get rid of some of that extra writing. Let's say I went to a negative cos curve. So I would then go through, doesn't affect it. I'm going to need a phase shift. Well, what does a negative cos graph do? Well, a cos graph normally starts at the top and falls, so a negative cos graph would start at the bottom and rise. Whereas the first instance where we are at the bottom and rising, all the way down there, I look up and see how far that is, and so therefore I would have to shift my graph all the way over there, which means I would have a shift right 3 pi by 10. So you take a look, there are 4 of the infinitely many possible equations that we could build. We haven't even addressed shifting it past this first cycle. We haven't addressed shifting it left instead. But those would be the 4 graphs or 4 equations where we could see each shift. Now, where I described, okay, in my mind, I want the ones that are the least amount of work. I want to go onto this page and I want to kind of show you what would be my ranking and how I would build the equations. So, number one, if I had to go through and build an equation, the one equation that I would build in this instance would clearly be my sine graph, because it doesn't require a phase shift. And I need to be more specific, a positive sine curve. It would not require a phase shift. To me, that makes that easier. Well, now you look at the rest of those equations, and they all require a phase shift. So how would I put in my mind the next equation that would be the least amount of work? And I know it's weird, but I view phase shifts like actual physical work. It's like I view having to move a curve, like the farther I have to move it, the more work it is. So if I only have to move it like a short amount, somehow in my mind, that rings like it's easier. So in that instance, my smallest phase shift would be my positive cos curve. I only had to move it this much. Less work. I know it's weird, but that's the way my brain works. So then what would be my next one? Well, you take a peek and you notice that my negative sine curve would mean I would only have to shift it this far. And lastly, I would end up dealing with equation 4. Now, I also want you to notice that both equations in 3 and 4 both require a reflection in the x-axis. But somehow in my mind, a reflection is less work. Flipping your curve or reflecting it in the x-axis seems like less work than physically pushing it to incorporate a phase shift. I know it's weird, but in my mind, that's the way it goes. So what you'll see me tend to do is to kind of follow that order. I don't mind reflecting if it gets me a shorter phase shift. Okay, let's jump into another. So what I'd like you to do is I would like you to take a look at the graph that you see on the screen, and I'd like you to go start to finish on this one. So let's see if we match up. Remember, we have to build a sine equation and a cosine equation to match that graph. So pause the video now, give it a shot. Okay, and hopefully we're back. And so I can go through and I can label out a bunch of properties. If I take a look at this, that gets me down to a -4 minimum value and up to a 2 maximum value. So that's what's going to tell me that my amplitude is 3. If I were to move 3 units down from 2 or up 3 units from -4, that's going to get me a vertical shift by a factor of -1. Gets me to my middle of my graph at -1. I take a look at examining my period. Well, where the middle of the graph I just found was -1, I start at -1, and so as I work my way through and get back to -1, falling, rising, falling, I see that my period is 4 pi. And so maybe pretty quickly, we could then go through and say that your k value, my normal period would be 2 pi. I've clearly stretched that by doubling it. Therefore, my k value would have to be 1/2. Or again, we're saying that my period of 4 pi has to equal 2 pi over k. Multiply out your k, divide out your 4, and we come in on a value of 1/2. So we have everything that we need right there to be able to build the equation. So let's build it. So the first thing I want to look for is my starting value. And my curve starts in the middle and falls. That would match a negative sine graph. So my first instinct then is to use a negative sine curve. That way I would not require a phase shift. So I can plug in my amplitude. I can see my stretch factor horizontally, my k value. There is my independent variable. Subtract off 1 and we're good. Okay, now I have to build a cos graph. Well, this is one of those instances where I say, I know it's a little bit weird, but the first max or min value that I encounter is this point here that would have an x value of a pi. It's a minimum value. Well, I know that I can get to that minimum value pretty quick if I reflect my cos curve. Reflecting my cos graph puts me on the bottom, rising, which is just like what's happening at my minimum. So if I deal with my amplitude and my stretch factor, then I notice that all I have to do is shift that curve to the right pi units. Those would be the first two graphs I would expect to see. It's not that they're more correct. The green one is clearly easier to come up with because there's no phase shift. However, the other two equations you could have come up with would be pretty standard. That if I chose to use a positive sine curve, then positive sine curves start in the middle and rise. And so the first instance where I see a in the middle rising occurs at 2 pi. That means I'd have to shift my curve to the right 2 pi to get there. Or I take a peek and I say, well, maybe I just used a positive cos graph. I know that my positive cos graphs have maximums. They start at the top. And so if I was to look at where's the first instance where I start at the top, then it's way over here. Well, what's the x value at that? 3 pi. And so if I shifted it to the right, 3 pi, I would get there. Those would be the four equations that I would expect to see. Hopefully you gave me the green and then one of the other ones. If you did, I think we're doing great. Okay, here comes your doozy. So what you'll see then is we've jumped into a reciprocal graph. And I've asked you to come up with a cosecant and a secant function that's going to represent that picture. So I'm not changing anything on you because there really isn't a different process for this. However, what you've noticed is we focused in on maximum, minimum, and middle values on those previous graphs. Let's do the same thing for cosecant, secants. I'm just going to recommend to you, why don't we actually label the points? And so what I may do is I may take a look and say, well, here's a local min that seems to occur at 0, 1. Here is a local max that seems to occur at pi negative 3. And here is another local min that seems to occur at 2 pi 1. And just by labeling those points, I'm hoping some stuff jumps out at you. That we actually see a picture that doesn't require a horizontal stretch. That is, when we take a look at that graph, you notice that you have one complete cycle that takes place between 0 and 2 pi. So, right off the bat, we notice that our k value is 1. The other thing I'd like you to notice is that although this is not an amplitude, because it's not half the height, that you have a distance of 1 down to negative 3, you have a distance of 4 between your curves. On your normal cosecant or secant function, you go from a minimum of 1 to a maximum of negative 1. And so that distance is normally 2 units. That what we've done is we've doubled the distance between our curves. That tells us that we've done a vertical stretch by a factor of 2. And therefore, our a value is 2. Okay, now we just have to go, what is the placement of that curve? Now, the other nice part is, when we take a look at this, and I'm just going to get rid of this, when we take a look at that graph, one of our graphs normally starts with a minimum and rises. We then jump down to the other branch, and we fall. Notice that we could create the equation to one of these equations by incorporating no phase shift. So what we need to do is to try to think back and say, well, which one of those graphs starts at 1 or starts at a minimum? Last part, as we take a look, we need to determine, was there a vertical shift at all? And since you notice that you have a distance of 4 in between, then if we split that distance and go up 2 units or go down 2 units, we will arrive at the middle of that graph. And so we notice then that we have a C value of -1. We have shifted our curve down 1. Okay, I think we have everything we need on that picture to be able to go through and create the equation. So, as I go through to create that equation, I've got some standard stuff. I know that I have an A value. I'm now trying to decide cosecant. I have possibly a phase shift, possibly not, shifted down 1. Or I have my secant graph. Possible phase shift, possibly not, shifted down 1. So as we go back and we consider the starting point, I know that my cosecant graph normally starts at a minimum. Or I know that my secant graph normally starts at a minimum. I have to go back to thinking about that curve. And one of the things that can help us is to actually picture your primary graph. If we're having a tough time remembering that, what I'm going to do is just erase all the writing on the page, and I'm going to draw in my primary curve. My primary curve that would match this graph would be something that would go from a minimum, down, hit the maximum, come up, hit the min. And maybe you can now see that the curve that I actually drew to match its starting point would be a cos graph. And therefore, I can eliminate a phase shift if I use the reciprocal of my cos curve. I'm going to use my secant. So the easiest equation for me to build then would be to go through and use a secant. Okay, now I'm going to get rid of that cos curve I drew because we know that our cosecant graph is the one that's going to require a phase shift. One of the properties that I haven't even touched yet of that curve, but that can be very, very helpful for us to determine stretch and phase shift, are your asymptotes. And you'll notice that you have an asymptote at pi by 2 and an asymptote at 3 pi by 2. Well, if you start to think back to where are your asymptotes on your cosecant graph, then you would normally have a cosecant graph that would have an asymptote at 0, an asymptote at pi, and an asymptote at 2 pi. And so maybe we can see then that what we need to do is to shift that purple asymptote to the right pi by 2 to get it to lie in the correct position. By shifting it pi by 2 to the right, I will have also shifted the other one, and then clearly there's just an asymptote that I can't see. And that might really help us to come up with our proper shift. There you go. Us being able to take the equation and take the picture and be able to build an equation to it. That is going to become a super, super important skill as we move into our trig applications. So your job now, jump in, get some practice, and make sure we're good. Good luck.